Earth's geophysical crisis is more serious than scientists expected. Beneath our feet, far below the cities we build and the roads we travel, forces are moving that we rarely think about. The ground feels stable, the mountains look permanent, the oceans seem timeless, yet the planet we call home is not a fixed object. It is dynamic, restless, and constantly evolving. And today the evidence suggests that Earth's geophysical condition may be more serious than many scientists once believed. For decades, researchers have monitored seismic activity, volcanic eruptions, magnetic field fluctuations, tectonic plate movements, and oceanic shifts. These processes are not new. They are part of Earth's natural cycles. Our planet has always changed. Continents drift, poles wander, ice ages come and go. But what concerns experts now is not the existence of change. It is the rate, intensity, and interconnected nature of these changes. Seismic data reveals increasing clusters of powerful earthquakes in certain regions. Volcanic systems that were once considered dormant are showing renewed activity. Deep beneath the surface, magma chambers shift and expand. Tectonic stress builds along fault lines that have remained quiet for generations. While none of these phenomena alone signal catastrophe, together they paint a picture of a planet under mounting pressure. At the same time, Earth's magnetic field, our invisible shield against solar radiation, is weakening in measurable ways. The magnetic poles are drifting faster than expected. Regions such as the South Atlantic anomaly show unusual reductions in magnetic strength. Satellites passing through these areas experience higher radiation exposure. Scientists debate whether this represents a temporary fluctuation or part of a longer geomagnetic transition. The magnetic field has reversed many times in Earth's history, but if such a shift were to accelerate, it could have significant implications for modern infrastructure dependent on satellites, power grids, and communication systems. Ocean currents, too, are displaying signs of instability. Major circulation systems regulate global climate by distributing heat across the planet. Subtle disruptions in these currents can influence weather patterns, storm intensity, and regional temperatures. When oceanic systems shift, atmospheric behavior responds. The result can be extreme weather events that strain ecosystems and human societies alike. Glacial melt contributes another layer of complexity. As massive ice sheets lose volume, weight distribution on the planet changes. This redistribution affects crustal stress. In some regions, the removal of ice mass allows land to rebound upward, subtly altering tectonic balances. Even small shifts in stress can influence fault systems already near critical thresholds. What makes the current situation particularly serious is the interconnectedness of these systems. Earth is not a collection of isolated mechanisms. It is an integrated system. Changes in one domain ripple into others. Solar activity influences the magnetosphere. Magnetic variations affect atmospheric chemistry. Ocean temperatures influence seismic pressure through thermal expansion and crustal loading. The boundaries between geophysical disciplines are becoming increasingly blurred. Modern technology has allowed scientists to observe the planet with unprecedented precision. Satellite arrays track millimeter-scale ground deformation. Seismographs detect vibrations from the other side of the globe. Deep-sea sensors monitor temperature and salinity changes in real time. These instruments are revealing patterns that were invisible just a generation ago. With greater visibility comes greater awareness, and sometimes greater concern. It is important to understand that Earth has endured dramatic shifts before. Supervolcanoes have erupted, asteroids have struck, magnetic reversals have occurred, life has persisted through immense upheaval. The planet itself is resilient, but human civilization is structured around stability. Power grids, transportation networks, food systems, and communication infrastructure depend on predictable conditions. When geophysical volatility increases, vulnerability rises. The seriousness of the situation lies not in a single catastrophic event, but in cumulative stress. Multiple systems experiencing heightened activity simultaneously increase uncertainty. When seismic strain, magnetic variation, climatic shifts, and oceanic instability overlap, forecasting becomes more complex. Preparedness becomes more urgent. Some scientists emphasize caution in interpreting trends, noting that Earth operates on timescales far longer than human observation records. A century of data may not capture full planetary cycles. Others argue that rapid technological advancement has simply improved detection, making natural processes appear more dramatic than they are. These perspectives remind us to avoid sensationalism, yet caution does not negate responsibility. Monitoring, research, and infrastructure resilience are essential. Understanding geophysical patterns allows societies to adapt rather than react blindly. Investment in early warning systems, grid protection against geomagnetic storms, earthquake-resistant construction, and climate-resilient planning reduces risk. There is also a deeper realization emerging from this growing body of data. Humanity is not separate from Earth's systems. We are participants within them. Our technologies rely on stable magnetic fields. Our agriculture depends on predictable seasons. Our communication networks orbit within vulnerable magnetospheric zones. The more advanced our civilization becomes, the more sensitive it is to planetary variability. The phrase "more serious than scientists expected" does not imply inevitable disaster. It reflects the recognition that Earth systems are dynamic and, in some respects, accelerating beyond earlier models. Scientific understanding evolves. Predictions are refined. New data reshapes assumptions. What once appeared gradual may now appear more urgent. This moment calls for perspective rather than panic. It calls for humility in the face of planetary forces that operate far beyond human control. It calls for collaboration across disciplines, nations, and institutions to better understand and prepare for geophysical realities. Earth has always been active. What has changed is our awareness of its complexity and our dependence on its stability. Beneath our feet, tectonic plates continue their silent movement. Above us, the magnetosphere flexes under solar influence. Oceans circulate, ice shifts, and deep interior processes churn. The seriousness lies in recognizing that these forces are not distant abstractions. They are ongoing, measurable, and increasingly significant in a world where billions of lives are interconnected through fragile systems built upon the assumption of stability. Earth's internal forces are not static mechanisms quietly operating in isolation. They are dynamic systems driven by immense heat, pressure, rotation, and gravitational interaction. Deep beneath the crust, the mantle slowly convects, transferring heat from the core toward the surface. The outer core churns with molten iron, generating the magnetic field that shields the planet from harmful solar radiation. Tectonic plates drift across the surface, colliding, separating, and sliding past one another. These processes have existed for billions of years, shaping continents, raising mountain ranges, and forming ocean basins. What is drawing increasing scientific attention today is evidence suggesting that some of these internal forces may be intensifying or behaving in ways that exceed earlier projections. Seismic records collected over the past century reveal fluctuations in earthquake frequency and clustering patterns. While earthquakes have always occurred, researchers now observe certain regions accumulating stress more rapidly than models once anticipated. Megathrust fault zones, where tectonic plates converge, display signs of strain buildup that could release enormous energy. Instruments capable of measuring ground deformation at millimeter precision show subtle shifts along fault lines previously thought to be relatively stable. These measurements do not guarantee imminent events, but they highlight a dynamic system under evolving pressure. Volcanic activity offers another window into internal intensification. Magma movement beneath the crust generates measurable changes in land elevation, gas emissions, and thermal signatures. Satellite-based infrared sensors detect rising heat levels at volcanic sites worldwide. Some supervolcanic systems, long considered dormant, exhibit renewed signs of magma chamber inflation. In many cases, activity remains within normal geological variation, yet the scale and frequency of monitoring reveal complexities not fully accounted for in older predictive models. The Earth's mantle, though solid in composition, behaves like a very slow-moving fluid over geological time. Convection currents within the mantle redistribute heat from the core. Variations in these currents can alter tectonic plate motion. Recent geophysical imaging techniques, including seismic tomography, allow scientists to visualize density variations deep inside the planet. These images suggest plume activity. Columns of hot material rising from deep mantle layers may be influencing surface volcanism more actively in certain regions than previously understood. The core itself remains one of the least accessible and most mysterious components of Earth's structure. Composed primarily of iron and nickel, the outer core's liquid motion generates the geomagnetic field through the geodynamo process. Fluctuations in magnetic intensity and pole drift may reflect changes within this turbulent metallic ocean. Measurements indicate that the magnetic field has weakened by a small but measurable percentage over the past 2 centuries. The rate of pole movement has accelerated, suggesting dynamic processes within the core may be shifting in ways that challenge long-standing assumptions about stability. Internal intensification is not limited to tectonic and volcanic processes. Subduction zones where oceanic plates descend into the mantle store enormous energy. As slabs sink, they influence mantle convection patterns and stress distribution. Advanced modeling reveals that variations in slab density and angle can significantly alter stress accumulation rates. This means that even slight changes deep within the Earth can ripple outward to affect seismic potential near the surface. Another factor is isostatic adjustment. As glaciers melt and ice sheets thin, the removal of massive weight allows the crust to rebound upward. This vertical motion redistributes stress along fault systems. Regions previously compressed under ice may experience renewed tectonic activity as the crust adjusts. While this process unfolds gradually, it demonstrates how surface changes interact with deeper geophysical systems. Technological advancements have improved detection capabilities dramatically. Global positioning system networks track continental drift in real time. Ocean bottom seismometers record tremors beneath vast water expanses that were once silent in observational records. Gravity measuring satellites detect minute shifts in mass distribution caused by magma migration or groundwater changes. These tools reveal a level of internal complexity that older generations of scientists could only infer indirectly. It is important to distinguish between improved observation and true acceleration. Some increases in reported activity result from better instrumentation rather than actual intensification. However, statistical analyses indicate that certain stress accumulations and geodynamic shifts exceed earlier linear projections. Climate-driven surface changes may also interact with subsurface dynamics in feedback loops not fully understood. Solar activity adds another dimension. Powerful solar storms interact with Earth's magnetosphere, inducing electrical currents in the crust. While these geomagnetic disturbances primarily affect technological systems, they also highlight the coupling between internal magnetic processes and external cosmic forces. The magnetic field's variability suggests that Earth's deep interior is not in static equilibrium. Heat flow measurements from boreholes and oceanic ridges reveal ongoing redistribution of thermal energy. Mid-ocean ridges, where new crust forms, exhibit spreading rates that vary over time. Changes in spreading rates can influence global sea levels and crustal stress patterns. Though these changes are measured over decades or centuries, they contribute to a broader understanding that Earth's internal engine operates with fluctuations rather than perfect constancy. Supercomputer simulations of mantle convection show that small perturbations can amplify over time, altering plate dynamics. These nonlinear systems mean that internal forces may not progress smoothly, but can accelerate under certain conditions. Energy stored over long periods may release in clusters, creating sequences of significant seismic or volcanic events. The intensification narrative does not imply sudden planetary upheaval. It reflects an evolving recognition that Earth's internal systems are interconnected and sensitive to multiple variables. What once appeared predictable within narrow ranges now reveals layers of variability influenced by thermal gradients, compositional differences, rotational forces, and gravitational interactions with the Moon and Sun. As data accumulates, scientists refine models to account for complexities previously underestimated. The deeper we probe, the clearer it becomes that Earth's interior is not a slow, uniform machine, but a dynamic system capable of shifting behaviors. Patterns once interpreted as stable may, in fact, be part of longer cycles of intensification and relaxation, operating on scales beyond short human observation windows. Earth's internal forces continue their relentless motion beneath the surface, redistributing energy, reshaping boundaries, and generating the magnetic and tectonic dynamics upon which surface conditions depend. Enhanced monitoring and advanced modeling reveal a planet whose internal activity may be more variable and, in certain respects, more vigorous than earlier generations of scientists anticipated. Earth does not operate as a collection of isolated systems functioning independently from one another. Its structure is an intricate network of interacting components: tectonic plates, oceans, atmosphere, magnetic field, cryosphere, and deep interior processes, all influencing each other in subtle and sometimes dramatic ways. When multiple geophysical systems begin shifting at the same time, the implications become more complex than any single event in isolation. Tectonic movement is one of the most visible expressions of Earth's dynamism. Plates drift across the surface at rates comparable to the growth of human fingernails. Over millions of years, these movements reshape continents and oceans, yet tectonic motion is not uniform. Some boundaries accumulate stress quietly for centuries before releasing it in powerful earthquakes. Others experience slow slip events, gradual releases of strain that do not produce immediate destruction but indicate underlying adjustments. When tectonic stress patterns shift simultaneously across different regions, the global distribution of seismic risk changes. At the same time, volcanic systems respond to deep mantle activity and crustal pressure variations. Magma chambers inflate or deflate depending on heat flow and stress conditions. Increased seismicity beneath volcanoes can signal magma migration. Gas emissions such as sulfur dioxide fluctuate as conduits open or seal. When tectonic stress increases in one region, it can influence neighboring volcanic systems by altering crustal tension. These interconnected adjustments demonstrate that plate movement and volcanic behavior are deeply linked. Earth's magnetic field represents another shifting system. Generated by convection in the liquid outer core, it protects life from harmful solar radiation. Observations show that magnetic pole drift has accelerated in recent decades. Field intensity varies across different regions of the planet. The South Atlantic anomaly, where magnetic strength is weaker than average, has expanded and shifted. Although geomagnetic variations are natural, their timing alongside other geophysical changes prompts closer examination of core dynamics and their potential interactions with surface systems. Ocean circulation patterns also show signs of variability. Major currents such as the Atlantic meridional overturning circulation redistribute heat globally. Subtle temperature and salinity changes can influence the strength of these currents. As polar ice melts and fresh water enters the oceans, density gradients shift. These changes affect how deep water forms and sinks, which in turn influences global heat distribution. When ocean currents fluctuate, atmospheric patterns respond. Storm tracks alter. Drought and precipitation zones shift. Climate variability intensifies. Glacial retreat adds further complexity. Massive ice sheets exert tremendous weight on the crust. As they thin, the underlying land slowly rebounds upward in a process known as post-glacial isostatic adjustment. This rebound changes stress distribution along faults, Regions once compressed may experience renewed seismic sensitivity. The redistribution of mass also subtly affects Earth's rotation and gravitational field, illustrating how surface changes can cascade into broader geophysical systems. Atmospheric shifts are closely connected to oceanic and cryospheric changes. Warming temperatures alter wind patterns and jet stream behavior. Altered jet streams can influence pressure systems that interact with tectonic regions prone to landslides or erosion. Heavy rainfall events increase groundwater infiltration, which in some areas may affect fault lubrication. Though such interactions are complex and not fully understood, they reveal how multiple Earth systems operate within a web of feedback loops. Solar activity introduces another layer of influence. Periods of heightened solar radiation interact with Earth's magnetosphere, generating geomagnetic storms. These storms induce currents in the ionosphere and occasionally in the crust. While primarily affecting technological infrastructure, such disturbances also highlight the sensitivity of Earth's magnetic system to external forces. When geomagnetic fluctuations occur alongside tectonic or atmospheric variability, researchers explore whether shared underlying cycles or coincidences are at play. Technological advancements have made it possible to detect simultaneous shifts with remarkable precision. Satellite gravimetry measures changes in Earth's gravitational field caused by mass redistribution from melting ice or groundwater depletion. Interferometric synthetic aperture radar tracks minute ground deformation associated with tectonic strain or magma movement. Ocean buoys relay temperature and salinity data in real time. Seismic networks capture tremors too small for human perception. These tools reveal patterns of overlapping activity that were once invisible. The convergence of multiple shifting systems increases uncertainty in forecasting. Predictive models often rely on assumptions of relative independence between systems. When tectonic stress, oceanic circulation, atmospheric behavior, and magnetic variation change concurrently, models must account for cross-system interactions. Nonlinear dynamics mean that small perturbations in one domain can amplify changes in another. Historical records show that Earth has experienced periods of synchronized geophysical transformation. Mass extinctions, glaciations, and major volcanic episodes often coincided with tectonic rearrangements and atmospheric shifts. These past events unfolded over extended timescales, but they demonstrate the potential for systemic interaction. Modern observation compresses our awareness of change into decades, making simultaneous shifts appear more dramatic. It is essential to distinguish between natural variability and unprecedented acceleration. Earth's systems have always fluctuated. However, the increasing overlap of measurable changes raises questions about thresholds. Complex systems theory suggests that when multiple variables approach critical limits simultaneously, the probability of cascading adjustments rises. This does not imply inevitable catastrophe, but highlights sensitivity. Human activity intersects with these natural systems. Urban development in seismic zones, infrastructure dependent on stable magnetic fields, and agricultural systems tied to predictable climate patterns increase societal exposure to geophysical variability. When systems shift together, resilience depends on adaptive planning informed by interdisciplinary research. Scientific collaboration across fields has become increasingly important. Geophysicists work alongside climatologists, oceanographers, and space weather specialists to understand integrated dynamics. Data sharing allows patterns to emerge that might otherwise remain compartmentalized. The recognition that Earth's systems are interdependent encourages holistic approaches to monitoring and preparedness. As multiple geophysical systems exhibit measurable change, tectonic strain adjustments, volcanic unrest, magnetic pole drift, ocean circulation variability, and cryospheric mass loss, the picture that emerges is one of a planet in coordinated motion. These shifts may reflect long-term cycles, external influences, or internal feedback processes not yet fully resolved within predictive frameworks. What becomes evident through observation is that Earth functions as a unified interactive system where concurrent adjustments across different domains shape the conditions experienced on the surface. Modern civilization rests upon an assumption so deeply embedded in daily life that it is rarely questioned: stability. Cities are built on the expectation that the ground will remain steady. Power grids are designed with the belief that magnetic conditions will remain within predictable limits. Global supply chains depend on navigable oceans, functioning satellites, and reliable climate patterns. Communication networks assume atmospheric consistency and uninterrupted orbital systems. Yet this intricate web of technology and infrastructure exists atop a planet governed by dynamic geophysical forces that do not operate according to human schedules. Electric power systems illustrate this vulnerability clearly. High-voltage transmission lines stretch across continents, interconnected in vast grids that balance supply and demand in real time. These systems are sensitive to geomagnetic disturbances. When powerful solar storms interact with Earth's magnetosphere, they induce electrical currents in the ground. These geomagnetically induced currents can overload transformers, damage equipment, and trigger widespread blackouts. A sufficiently intense solar event could disrupt power on a continental scale, affecting hospitals, water treatment facilities, communication systems, and financial networks simultaneously. Satellites orbiting Earth form another critical layer of modern life. Navigation systems, weather forecasting, telecommunications, banking transactions, and military coordination depend on stable orbital operations. Variations in Earth's magnetic field and solar radiation levels influence satellite electronics and orbital drag. Increased atmospheric expansion during solar activity can alter satellite trajectories. Even minor disruptions in satellite timing signals can cascade into significant economic and logistical consequences given the precision required for global positioning systems. Urban environments amplify geophysical risk. Many of the world's largest cities are located near tectonic plate boundaries or coastal regions vulnerable to seismic and oceanic shifts. High-rise buildings, bridges, tunnels, and transportation networks concentrate population and infrastructure in compact areas. When seismic activity increases or fault stress accumulates, the potential impact on dense urban centers rises dramatically. While engineering standards have improved, older structures and rapidly expanding urban regions may not meet modern resilience criteria. Water systems are similarly dependent on stability. Reservoirs, dams, and aqueducts distribute water across vast distances. Changes in precipitation patterns linked to shifting ocean currents or atmospheric variability affect water availability. Drought conditions strain agricultural production and energy generation from hydropower. Heavy rainfall events increase flood risk, overwhelming drainage systems, and damaging infrastructure. The delicate balance between water supply and demand is sensitive to climatic and geophysical variability. Transportation networks depend on predictable environmental conditions. Aviation relies on accurate atmospheric modeling and stable navigation systems. Shipping routes depend on ocean current patterns and stable sea levels. Rail systems and highways are vulnerable to ground deformation from seismic activity or permafrost thaw. Even slight changes in land elevation can compromise structural integrity over time. The interconnected nature of transportation means that disruption in one region can ripple across global trade networks. Food production systems reveal another dimension of vulnerability. Agriculture depends on consistent seasonal cycles, soil stability, and water availability. Variations in climate patterns linked to oceanic and atmospheric shifts influence crop yields. Soil erosion can accelerate due to extreme weather events. Volcanic eruptions, while rare, can inject ash into the atmosphere, affecting air travel and altering short-term climate patterns. Globalized food distribution means that localized disruptions can have international consequences. Communication networks form the nervous system of modern society. Fiber optic cables cross oceans and continents, while wireless communication relies on satellite relays and atmospheric transmission. Geophysical events such as earthquakes can sever undersea cables, isolating regions from digital connectivity. Solar storms can disrupt radio communication and satellite operations. The dependence on continuous data flow means that interruptions, even brief ones, can affect financial markets, emergency services, and government operations.